Assalamu alaikum students. The topic of this presentation is coefficient of compressibility. Now you all know that volume or density of a fluid changes with the change in its temperature or pressure. When the fluids they can have expansion or they can have contraction by the application of pressure or the change in temperature. Now for a fluid, when you exert pressure on it, is at higher pressure, the volume changes decreases. When you reduce the pressure, it expands. So there is a relation between pressure and volume, and this fluid basically acts like an elastic solid. Elastic solid is when you apply some force, there is some deformation, and when you remove that force or reduce that force, it comes back to its original position. Now for that one, you have already learned about Hooke's law, where stress is proportional to strain by a bulk modulus of elasticity, which is K. Now the fluids, when you exert pressure on it, they are going to contract. When you reduce pressure, they are going to expand. But different fluids expansion and contraction varies uh, with the change in material. So for a same amount of pressure, for example water, that will have different contraction as compared to air. So we need some kind of coefficient to relate pressure and volume. For that one we use coefficient of compressibility. Now for bulk modulus of elasticity, you know it has stress, which is basically force per unit area, and the strain, in simple words, it's a change in volume per original volume. For fluids, this force per unit area is referred as pressure. So we need to find coefficient of compressibility that can relate pressure and volume. So this pressure and volume is related through this expression, where K is negative V node dP over dV at constant temperature. Now if you notice there is a negative sign here. This negative sign is brought in here to ensure that K has a positive value. Why? Because you know pressure and volume are inversely proportional to each other. You increase pressure, the volume is going to decrease. You decrease pressure, volume is going to increase. Now this this pressure, you know, it is force per unit area, and force is a vector quantity. So we want to ensure that this K is always positive, so we bring in a negative sign here to ensure that K has a positive value. Now this dP over dV times V with the negative sign becomes equal to rho dP over d rho at a constant temperature. How it is so? We all know that density is 1 over V. So if you take the differential of density, what it becomes, d rho is equal to dV over V squared with the negative sign. So basically dV is negative V squared d rho. Now you substitute that into this expression, the K becomes negative V dP over negative V squared d rho. Or you can say it becomes 1 over V dP over d rho. And 1 over V is basically rho. So K becomes rho dP over d rho at constant temperature. Now this K value, which is written in differential form, for finite changes it becomes del P over del rho del V over V. How it is so? Now the relationship between pressure and volume is not linear. For example, I just plot here. Here is pressure and here is volume. You increase volume, pressure decreases. You decrease volume, pressure increases, and say this is the curve that I get. Now if you look at here, it is not going to 0. Why? Because you keep on compressing. After some time, very high variation in pressure is required to change the volume. And the relationship between pressure and volume is not linear. Now you have the slope of this line which is changing. As you know, the slope is basically dy over dx in differential form. You have also learned in high school that for a linear line you can say slope is basically y2 minus y1 over x2 minus x1, or in other words m is del y over del x. You have learned this in high school already. Now for this non-linear line, I take a very small segment. Say I take a segment between these two lines. It looks linear. It is not non-linear between these two lines. If I make it a very small change, then it will become linear. When it will become linear, then we can apply del y over del x instead of taking the differential. That's why it is being written here that in terms of finite changes, we can just simply write dp over dv, which is basically the slope, as del p over del v. So k becomes negative del p over del v over v. Now if you look at this expression, it is quite similar to Hooke's law that you have learned, that we have studied, where the bulk modulus of elasticity was basically stress over strain. And I told you at that time that stress is pressure and strain is change in volume per original volume. In terms of density, it can be written as del P over del rho over rho at a constant temperature. And remember, we are discussing for a unit mass. That's why del V is basically del rho. Okay, I hope it is clear to you now. Now for ideal gas, coefficient of compressibility is equal to absolute pressure. How it is so? To understand this, you need to just remember about ideal gas law, which is P is equal to rho R T. If we take the differential at constant pressure, then dP over d rho at constant temperature becomes equal to RT, which is basically equal to P over rho. Now we apply this into coefficient of compressibility. We all know this K is basically equal to rho dP over d rho at constant temperature. Now this dP over d rho at constant temperature is basically P over rho for an ideal gas. So K becomes rho times P over rho. Rho cancels with rho and K becomes absolute pressure. Now second thing for ideal gas, that del rho over rho is equal to del P over P, and this particular thing we can get it from just remembering about finite changes. I just erase here. As we have learnt already that dP over rho at constant temperature is basically equal to P over rho for an ideal gas. For finite changes, this part becomes del P over del rho, which is basically equal to P over rho. And rearranging this will yield to this expression, which is del rho over rho is equal to del P over P. Now this expression shows that for an ideal gas, percent increase in pressure is equal to percent increase in density, or vice versa. Percent increase in density is equal to percent increase in pressure. In other words, if you increase the pressure by 1%, the density should increase by 1%. So this is the relation between pressure and density. What about volume? I leave it to you, and you need to explain me how this uh, pressure, density and volume relates for ideal gas law. And as I have said here that the percent increase in pressure is equal to percent increase in density, what happens to pressure, what happens to volume? Is volume going to behave differently at different pressures or no? So I leave it for you.